Okay, so Elizaveta Kononenko is our next speaker. She's going to be talking to us about 3D operando visualization of complex heterogeneous catalytic system using parahydrogen. Thank you so much for contributing to this PERM conference, and we're very excited to hear your talk. Thank you.
Thank you for introducing me. At the beginning of my report, I will talk about the relevance of this work. Then I will proceed to the use methods, such as NMR and MRI, FIB method. After that, I will talk about the results of this work, and I will move on to the conclusions. In my presentation, I will talk about the methods that we develop to study heterogeneous catalytic processes using spin hyperpolarization and MRI. Heterogeneous catalysis is the basis of most industrial chemical processes, including oil refining, the production of pharmaceuticals, detergents, and much more. So even a small increase in their efficiency can be economically beneficial. The simplest and most common type of heterogeneous reactor is a trickle-bed reactor. This type of reactor is a chemical reactor that uses the flow of liquid or gas up or down under the action of gravity or pressure through a packet layer of catalyst pellets. Although the principle of operation of the reactor is simple, but optimizing the operation of such reactors is still an actual task, because the heterogeneous catalytic processes is a complex combination, a lot of separate processes such as mass and heat transfer, in addition to the chemical conversion of reactants into various products and byproducts of the reaction. The information which is necessary to model the productivity of such reactors was formulated at the end of the 20th century. However, traditional measurement methods can provide only a rough approximation of the reactor work, because they are invasive and make changes to the studied system. Nuclear magnetic resonance method are particularly well suited for operando studies of catalytic processes due to the possibility of non-invasive visualization of chemical composition and mass and heat transfer processes in optically opaque system. However, the usual NMR measurement methods characterizes the entire sample, or that part of it that is located in the sensitive region of the spectrometer. So NMR measurement without spatial resolution averages the characteristic measured over the sample, while catalytic processes are actually heterogeneous, and spatial heterogeneity in itself is valuable information for us. The application of magnetic field gradient allows to restore information about spatial homogeneities, and therefore MRI is an important technique for studying heterogeneous catalytic processes. However, there are some drawbacks that significantly complicate such experiments. Their limitation that arises due to the low spin density of the reactants and products in the gas phase, as well as due to the inhomogeneity of magnetic field caused by the heterogeneous reactor. Moreover, of course, the low sensitivity of the NMR method associated with the small interaction of nuclear spins with an external magnetic field also delivers serious limitation on the applicability. However, one can overcome this limitation using methods of hyperpolarization, for example, parahydrogen induced polarization. This method allows to increase the NMR signal by several orders of magnitude, which leads to the possibility of MRI visualization of hydrogenation processes even in the gas phase. As we know, FIB is based on the pairwise addition of parahydrogen with their spin isomer of hydrogen to the substrate during hydrogenation. Because of their violation of the magnetic equivalence of the hydrogen nuclei, spin hyperpolarization is formed. The use of gaseous substrates and parahydrogen in combination with a heterogeneous catalyst is a simple way to obtain hyperpolarized products in the gas phase. In addition, in the case of studies of heterogeneous hydrogenation reactors, a significant sensitivity increase can be achieved by creating a reactor compatible with MRI studies. Typically, the reactor is a tube filled with catalyst pellets, which are usually various metals, and this type of reactor significantly distorts the uniformity of the magnetic field and leads to deterioration of the MR image or its complete loss. Therefore, it is necessary to create a reactor compatible with MRI studies in order to successfully use MRI to study catalytic processes. And at the beginning of 2019, it was shown that the use of glass tube with a thin layer of the active substance, rhodium-2, the titanium oxide, applied to the surface minimizes the disturbance of the magnetic field, which makes it possible to successfully perform imaging of heterogeneous hydrogenation processes, even with the use of normal hydrogen. In this work, we applicate and develop of MRI methods for spatial visualization of heterogeneous catalytic hydrogenation processes using parahydrogen. And in this work, unlike previous ones, we research the possibilities of the MRI method for studying a complex component hydrogenation, heterogeneous catalytic system. As a reactor, we used the glass tube. We prepared reactor by impregnation of silicon oxide to glass tube with the next impregnation of rhodium, palladium, and platinum active nanoparticles to the silicon oxide. 1,3-butadiene was used as a precursor to the hydrogenation reaction. And 1 and 2 butanes and the product of complete hydrogenation butane can be obtained in the hydrogenation of 1,3-butadiene. The spectra obtained during the hydrogenation of 1,3-butadiene at 70 centium degrees using parahydrogen and normal hydrogen are shown on the slide. The obtained spectra for the case of hydrogenation with parahydrogen, they show it that the palladium catalyst is the most selective for the formation of non-hyperpolarized butanes compared to others catalysts. The absence of hyperpolarized products also indicates an unpaired way of hydrogen addition. The most intense signals were observed for rhodium and platinum catalysts. However, these two types of catalysts didn't show any selectivity for incomplete hydrogenation products. That is, all reaction products were observed and all were polarized. To observe special distribution of reagents and reaction products, as well as to investigate the possibilities of the MRI to study a complex component system, 3 active components were applied in the following order: palladium, rhodium, and platinum on a glass tube coated with a thin layer of silicon oxide to the outside. To carry out the experiment, a capillary was passed through the inner part of a 5 millimeters reactor to the bottom of 10 millimeters NMR tube, through which a mixture of 1,3-butadiene and parahydrogen flew. Then, after optimization of pulse sequence parameters, MRI of 1,3-butadiene hydrogenation reaction was performed using the true-FISP pulse sequence in pseudo-3D mode. 8 3 millimeters two-dimensional slices were detected one by one and then converted to a 3D model using MATLAB software. For the analysis, the intensity of each pixel obtained during MRI of 1,3-butadiene hydrogenation with normal hydrogen was subtracted from the corresponding pixel obtained in the experiment with parahydrogen. And after that, to obtain special information about the formation and consumption of products along the catalyst layer, the intensity of each pixel of the previous layer was subtracted from the intensity of each pixel of the current layer. So we got the areas of formation which are indicated by blue, and areas of consumption are red. The use of selective pulses made it possible to visualize products not only separately from each other, but also to obtain special information about their distribution. And it was found that one butane is formed mainly on the rhodium catalyst, which is consistent with the results of spectroscopy. As regards hyperpolarized butane, it's preferably formed on palladium catalyst and less on platinum. This distribution of products indicates a high conversion rate on the palladium catalyst, and also the red region of butane consumption in the rhodium to the silicon oxide catalyst region indicates the relaxation of the hyperpolarized butane formed in the previous layer, which agrees with the results obtained using normal hydrogen. Thus, the obtained results clearly indicate the possibility to use MRI as a highly sensitive method for investigations of catalytic hydrogenation processes in situ. Moreover, selective visualization of reaction products over the catalyst make it possible to obtain unique information on the formation of a particular product with a special resolution. In conclusion, I would like to say that we developed a technique for conducting an experiment for selective MRI of the selective hydrogenation reaction of 1,3-butadiene in the gas phase. Also, we tested a catalytic system with active components platinum, palladium, rhodium deposited on the surface of silicon oxide. And it was found that in the hydrogenation reaction of 1,3-butadiene, palladium catalysts are most selective to formation of butanes, while catalysts with platinum and rhodium nanoparticles showed their maximum polarization. And MRI visualization of the distribution of products along the catalyst layer in a hydrogenation reaction using parahydrogen was demonstrated. Also, I would like to acknowledge to Igor Koptyuk, Kirill Kovtunov, and Alexandra Svyatova, and to the entire team of the Laboratory of Magnetic Resonance Microimaging, and also thank you for your attention.
Thank you very much. That was a very nice presentation. So there are a number of questions that come up. One is about slide number 7. Do you maybe want to go back to slide number 7? So the question is there some proof of exchange between 1-butene and 2-butene on the surfaces?
We don't have proofs, but we
yeah, it could be quite possible, right? That there's some exchange on the surfaces.
Yes, in this the high temperature, it is possible. So we didn't. Yes.
Yeah. No, I think your data is super interesting, and I think with some investigation of the question, one might be able to find out if there is exchange or not. So that's really good. So the next question is, can the products diffuse back through the capillary? And if they diffuse back, is there a possibility that the downstream catalyst would be interacting with partial hydrogenation produced from the previous platinum reaction?
We proved that diffusion through the capillary didn't exist because about it Alexandra said we performed the experiments with Teflon tube and proof that then they're not diffusion down on the tube.
Yeah, that's great. That makes good sense. I actually just got a message here from somebody else that says this bond migration question that we were discussing just a moment ago is very well known on metals, and it occurs very often. So it's probably quite likely that it's happening. So that's great. Okay. Well, thank you so much for such a wonderful presentation. Great work.